In this lecture, we will talk about broadcasting of NumPy arrays. So broadcasting allows an operator or a function to act on two or more arrays to operate, even if these arrays do not have the same shape. So two arrays can be subjected to broadcasting when all their dimensions are compatible, i.e. the length of each dimension must be equal or one of them must be equal to 1. So if neither of these conditions is met, you get an exception that states that the two arrays are not compatible. So in this case, we have to reshape one of the arrays to get compatibility for addition or calculation between two arrays. So when the rule of compatibility is met, then the size of the smallest array will be expanded to the size of the biggest array, so that the element-wise function or operator is applicable. For example, A is a matrix 2 by 2, the shape 2-dimensional array. Then B is a 1-dimensional array with 4 elements. Therefore, we write A plus B. Now that the two arrays have the same dimensions, after broadcasting, the values inside can be added together. We see this diagram. First, B will be broadcasted with 2 by 2 2-dimensional array, with the second, third, and fourth row will be the same as the original 1-dimensional array. Then the addition will be applied with element by element between two arrays. And broadcasting with U function, we can demean each column of an array by subtracting the column means. So for example, AI is an array 2-dimensional with shape 4 by 3, so 4 row, 3 column. If we write AR.mean, this is a U function applied by column or row. So here we add 0 in the parentheses, means to get the mean value of this array by columns. So each column will get the mean value because there are 3 columns here. So this will get a 1-dimensional array with 3 elements. Then we can write ARR, this array 4 by 3 minus this one. This is the value of the column of this array. So the broadcasting compatibility matches because 1-dimensional will be 1. Then broadcasting will apply for this calculation, and the result will be also a 4 by 3 array, and with each column of this array will be minused with this vector, with this 1-dimensional array. And after that, because this demeaned is also a 4 by 3 array, if we write again with the mean for this column, and the result will be 0 because this has been demeaned. So the mean of this demeaned will be 0. We will show later in code. And if we want to demean each row for the array, the mean vector by rows should be reshaped first before doing calculation, which is different from the previous example for demean by column. So again, this ARR is a 4 by 3 2-dimensional array with a random number. Inside, then we can write array.mean parenthesis 1. This is by row. So this will be created with a 4 by 1 array, because 4 row in this original array. So the mean value will create it for each row. So the result will be 4 comma 1-dimensional array. So if we write now ARR minus row means the reshape, we have to add a reshape to 4 by 1 first before do the minus calculation. then it will be okay. So the result will be also 4 by 3 dimension, but the value is minus by the mean value of each row in this original array. Then next, if we write the mean this 4 by 3 dimension array with a dot mean, also parenthesis 1 for the mean value for this row again, and the result will be all 0 because this has been demined along the row. Of course, mean value of demined will be 0. We will show later in the code. And using NP new axis function to reshape NumPy arrays. So in the 3-dimensional case, broadcasting over any of the 3 dimensions is only a matter of reshaping the data to be shape compatible. Using reshape is one option. But NumPy arrays offer a special function np.newAxis along with full slices to insert the new axis. What this means? Because in the 3-dimensional case, often the compatibility of broadcasting will not apply. So we have to reshape 2 arrays to the same size, same shape. So for example, here array is a 2-dimensional array with shape 4 by 4 with a value 0 for each element. Then we can write ARR_3D to reshape this array to the 3 dimension. How to do that? We just write the first with a colon inside the bracket, colon for the first dimension, then comma, and this colon for the last dimension, and between these 2 comma, we can add np.newAxis. So the result will be a 3-dimensional array with the shape 414, and the value 16 value will be the same as these values in the original 2-dimensional array. So if we write dot shape for this array, will show 4 by 414. Then next, we can create a 1-dimensional array for the random normal distribution number with 3 elements for 1D. Then we can similarly in the bracket, then write a colon here, then the comma, and new np.newAxis here. Then it will be a 2-dimensional array with the shape 3, 1. This column will get all the elements in the original array. And if we write the column next, then it will be created with a 1 by 3 2-dimensional array. So that if we had a 3-dimensional array and want to demin axis 2, say we would need to write, for example, this is a 3-dimensional array with a shape 3, 4, 5, and if we want to get the mean value along this axis, so we have to write a dot mean by 2 in the parentheses. Then this mean called the depth mean array, the shape will be changed to 3 by 4 because the last dimension has been meaned out. So next, if we want to minus this 2-dimensional array from this original 3-dimensional array, we have to reshape first. But how to reshape? We can use new access function. Here it was clear because the 2-dimensional will get all the value of this mean value. Then we just write np.newAxis. So this mean value of the original array will be reshaped to 3 dimensions, and the last dimension is only for broadcasting. So next, so this is compatible for calculation for minus, and of course the result will also have the shape 3, 4, 5. Then we can next calculate again the mean value of the last dimension. Then the value will be 0. We will show all this in Anaconda Spider now. So we see the file called section 10 the NumPy library.py, and the links to this file will be put in description of this video. So first we move to lecture 7 broadcasting. So first import NumPy as np, and we create 2 array. One is 2-dimensional, one is 1-dimensional. So we show A 2-dimension and B 1-dimensional. So A plus B this will be 2-dimensional, because this 1-dimensional will be broadcasted to a 2-dimensional with the same row, same for row for to 2-dimension. Then element-wise addition, and we should demean each column of an array by subtracting the column means. So first, this is a 4 by 3 2-dimensional array. 4 by 3. Then we can calculate the mean value by column. Column 3, column 1, 2, 3. Then 3 value, 3 mean value. Next, we can calculate and minus the mean value for each column. So each column will be minused with this. This column will be minused with this value. This one will be minused with this value, and so on. Then we see demeaned after the minus. This is after the minus for each with the column mean. Next, we show the mean value again for this column after the mean. So the result will be very, very small. Minus 17, minus 7. This is exponential description for the number. Actually 0. Very, very small. And similarly, we can calculate the mean by rows. So first, the original array is the same original array. Same as the original array. Then we can calculate the row mean for this array, and the row mean shape 4 elements. Because it has 4 rows for the original array. Then before we do the calculation for the minus of the original array and to minus the mean value of by row, then we have to reshape first. Reshape these row means. So here we use the reshape first before, then it's OK. Then next we see demeaned matrix. This is demeaned. Each row has been minused with the mean value of this row. Each row has been minused with the mean value of this row. So next we will show the mean value of this row again. Of course it will be 0. Very, very small number will be 0 because demeaned. So broadcasting with higher dimensions using NP new axis function to reshape. Yeah, first AR is 2-dimension array. Two-dimensional array ARR 0, all the value 0. Then we can use new access function to create a new array with three dimension, but the value are the same as this two-dimensional array. Yes, ARR 3D. Can see the value 16 values there, but now it's three-dimensional. You can see three brackets. So this is one dimension long, then next second dimension, and one bracket inside the third dimension. And show the shape. Shape now is 4, 1, 4. And we create a one dimension random number array. One dimensional. This is one dimension. Next, we will change to two dimension with the NP new axis right in the second dimension. So now it will be two dimension array and show the shape 3 by 1. So 3 row and inside of each row is only one value, one column. And similarly, we can change it to dimension 1, 3 with NP new axis in the first index in the bracket. So dimension is 1, 3 now. So if we have a three-dimensional array and wanted to dimension along the axis 2 is the last dimension. So first we create a three-dimensional array with random number. Show a three-dimensional array. Totally has 60 elements. So it has three brackets. First dimension, the shape first dimension has this one inside the first dimension, this block. Second block. Yeah, three block, and inside each block there are 4 by 5 two-dimensional array. So totally there are three-dimensional array. So next we will create a means along the last dimension, and the result will be a shape of 3 by 4 two-dimensional array. We'll show. So this is the mean value, and the last dimension has been meaned out. Now will be 3 by 4, lower dimension now. Three by four, because the last dimension has been meaned out. This is the mean value. This is the mean value along the last dimension. And next, if we want to calculate a regional array with this mean value along last dimension, then we have to add a new axis again before we can do the calculation. Otherwise, it's not compatible along the shape. So next we will do this. And the result called dimension is also a 3 by 4 by 5 three-dimensional array. Also three-dimensional array, three bigger block. The inside block will be 4 by 5 two-dimensional array. Then we can calculate again the mean value of the last dimension of this dimensioned three-dimensional array. We'll see how it is going. Then the value will be 0 and a very small number, 70, because it's just a computer storing numbers mechanism. Actually, it's 0. Very small, -7, -16, and there's 0. So because this has been dimensioned of course, the mint metric, the mint array's value is 0.